Good morning. This is organic chemistry lecture, I guess 1, 2, 3, 4. And today is Thursday, September 3rd, and we're going to be talking about resonance. Resonance is the cornerstone of organic chemistry, and especially curved arrows. So what you see today, you really want to work hard on. You want to practice as many practice problems as you can. We're finishing up chapter 2 today. It's officially sections 2.7 through 2.11. Section 2.7 is Introduction to Resonance. I will do that briefly on the board, and then I'll switch to an iPad to very carefully show you things. Print out the accompanying practice worksheets so you could follow along. There's a lot of doing and mimicking and behavior of the procedure of generating and drawing additional Lewis structures for things. So section 2.7 is Introduction to Resonance. Section 2.8 is Curved Arrows. Section 2.9 is Formal Charges in Resonance Structures. And section 2.10 is Drawing Resonance Structures via Pattern Recognition. And section 2.11 is Assessing Relative Importance of Resonance Structures. Okay, so on the board here behind me, I'm going to briefly introduce the why of resonance, and then I will switch to an iPad and show you how to draw resonance structures. All right, so let's discuss a little bit about resonance. If you have a p orbital, we oftentimes shade one of the lobes, but this just represents the phase of the orbital. It's not really significant which side is red, which side is blue. And if you have two electrons that reside in the p orbital, it's possible to put those two electrons in the top lobe. It's possible to draw two dots on the bottom lobe. And if you really wanted to, you could put one dot in either of these lobes. These are specific instances in time where you might find those electrons. But again, we know that electrons are like waves, and they're electron clouds, and they just fill the lobes of the p orbital, equally in probability. These would be represented as resonance structures. We have many different arrows in organic chemistry. This one is reserved for resonance. It means it's an equivalent electronic seating chart, or representation. Okay, as you know, in Lewis structures, you have to add the dots, and it doesn't matter where you put the dots, right? So, for example, hydrogen has one valence electron. It's okay if you put the dot on the right. It's okay if you put the dot on the left. It's okay if you put the dot on the top. It's okay if you put the dot on the bottom. All of these are the same thing. It's hydrogen with one valence electron. And we know that that's just a very limited representation of what the atom really looks like, which we really don't know what the atom looks like. But we think it's an electron cloud. It's a fuzzy object, right, where the electrons spread out, and there's a possibility of finding it to the north, the east, the south, the west, right? Now, what about a pi bond? Now, remember from our previous discussions in the class, a pi bond is an orbital overlap between two p orbitals on adjacent atoms. And a pi bond is two electrons, okay? Any bond is two electrons. So we want to put two electrons in here to describe that bond. Now, in the textbook, they might show one electron in this p orbital on the top lobe, one electron on the top lobe of this p orbital, and that's the pi bond, for example, in ethylene. So these two p orbitals might be on a carbon atom that's sp2 hybridized. It has a leftover p orbital, and there's one electron on that carbon, one electron on that carbon, and that forms the double bond, or the pi bond, in ethylene. Now, can we say always that that electron is going to sit and stand right there? No, it's possible that the electron could be in the bottom lobe. So at any moment in time, it could look like that. If you had a fast enough camera that could actually show you where the electron is, it's possible that it could be, both of them could be on that side at any one moment. That's possible. And that's possible as well. Okay, now this possibility and this possibility is not very likely because electrons like to spread out. So the most likely scenario is probably you're going to have something like this and something like this. Okay, now don't memorize these. This might be kind of confusing at this point, but my main point is that electrons are spread out. They like to hop around a lot, and they can explore different atoms. And we can't really say that it has a definite seating chart and the electron's always going to be over there. At any instant in time, it might be over here, it might be over there. Okay? Now we like to generate and draw resonance structures that contribute to the overall resonance hybrid. Let's review that you've learned in general chemistry so far. The acetate ion The acetate ion can be drawn in one of two different Lewis structures. When you're positioning things, you can make this oxygen pointing up a double bond, and this one have another additional lone pair compared to that one, and a negative charge. Or you can put the negative formal charge on the top oxygen and the double bond somewhere else. Resonance structures differ by the position of a lone pair and a pi bond. And one way to draw additional resonance structures is to move them using curved arrows. Curved arrows are a great way to generate and draw additional resonance structures. So I'll just show it really quick, but the other videos are going to go through it step by step by step and exactly show you what's going on. So you'll see this a lot in the textbook. The resonance arrows means this is a fake structure, this is a fake structure. The real molecule is like a hybrid of the two. In general chemistry, we discussed carbon-oxygen double bonds, and we said double bonds are shorter because there's more electrons bonding them. And carbon-oxygen single bonds are just single bonds, so they should be longer. And let me show you a bond strength table, well, in a bit. But what is this carbon-oxygen bond length? Is it short here and then long here? Is it fluttering back and forth? So if you had a fast enough camera and you made a movie, would this oxygen atom be going big and small, then big, then small, you know, for the bond length? Because a carbon-oxygen bond length should be small, and a carbon-oxygen bond length should be long for a CO single bond. So there is only one structure. The electrons are whizzing around, and what you have is an average of these, a weighted average of these two structures, depending on which one's more favorable or not, okay? And we would expect that the real structure is intermediate between these two extremes. So, you know, a kind of a very general analogy would be if one structure looks like this and another structure looks like this, the real structure isn't this, it's not this. You know, if you merge these two structures and average them, you know, then it would be a spork, right? So this could be a resonance structure, this could be a resonance structure, these could each contribute to the overall resonance hybrid, and the real resonance hybrid is going to have characteristics in between the two extremes. So let me take this tripod over here to this side of the board and show you this bond table to help solidify this fact for you. These are bond lengths in a unit called the angstrom. It's like the Oakland Athletics kind of symbol. It's an A with a circle on top. And and that's 10 to the minus 10th meters. So we're talking extremely small distances here. And I wanted to point out what a typical carbon-oxygen pi bond length is. It's 1.22 angstroms, so that's going to be short in comparison to a carbon-oxygen single bond or a carbon-oxygen sigma bond. The single bond is a little bit longer, okay? So this is shorter, double bonds are shorter, single bonds are longer. And then we have the acetate structure. In one of the structures, we have the oxygen with a double bond, and then the other structure, we have oxygen with a single bond. So do we see two bond lengths in the acetate ion? The answer is no. What's experimentally observed is that there's one bond length, okay? It's 1.272 angstroms for both this bond and this bond. And this structure here is a little bit fake, all right? It's a lie. The real resonance structure doesn't have a double bond here and a single bond here. It's an average of two things. You have to mentally imagine, well, that's the spoon. The other one would be the fork, and the real molecule is a spork, where the tines, you know, the length of the tines on the fork is intermediate between the two extremes. And if you look at the bond lengths, they're in between 1.2 and 1.4, right? It's, you know, 1.3 about, okay? So the bond lengths are intermediate between those two extremes, and there's only one bond length. Also, the charge is equally spread between the two oxygen atoms. If we come back to the acetate ion, we know that electrons have no seating chart, and half the time, perhaps the oxygen would be negative on this one, and half the time it would be neutral on this one over here, okay? So this oxygen is -1, this oxygen is 0. So if we average these two structures, and instead of taking a really fast picture, say we had a camera that could detect where charge is, and we held it down for, 5 seconds, and we just took an image of the acetate ion over time, we would see the structure that looks like this. We would see, this carbon would always be here, these atoms would always be here, and we would find that there's a -1/2 on average charge on this oxygen and a -1/2 charge on average on that oxygen. And how do we show that there's not quite a double bond here, but somewhere in between a single and a double? You can use dotted lines. Sometimes especially in inorganic chemistry, they show this kind of thing, okay? It's in between a single and double bond here, it's in between a single and double bond there, okay? So it's 1.5 bonds. This is too difficult to draw with a Lewis structure, right? It's a little bit hard to do that. So what we do in organic chemistry is we draw individual contributors. So this would be an individual contributor. This would be an individual contributor. And this thing down here that's, the real molecule that we have trouble drawing with the Lewis structure kind of technique would be the resonance hybrid. In some reactions in organic chemistry, it's critical for us to put the charge here so we could say, hey, there's a reaction happening on that oxygen atom. Other times we want the charge to be here so we can say, hey, look, this is what happens down here on the molecule. So we have to be able to draw these curved arrows. These ones in blue are curved arrows, and generate a new resonance structure. This is a resonance arrow to make that, okay? This arrow does not mean equilibrium. It's not fluttering between the two. We don't have an average of these two concentrations in solution. Neither of these two in boxes can be isolated. We can't isolate the average. That's the real molecule. And these in boxes are just fake pictures at any moment in time that help us move and account and keep accounting of electrons and where they're moving in a chemical reaction. So this arrow here means resonance. It means equivalent. Okay, this is equivalent to that. They're individual contributors, okay? So electrons have no seating chart. We can draw them all over the place, and that's kind of a little bit why we need to worry about resonance.